And there's some material from chapter 19, which I placed up on UTS Online, but I don't really like very much of it. I put it there in any case, but I think they tend to get confused when they talk about embedded systems and real-time systems, which is not helpful. But they introduced the ideas pretty much in a reasonable way. And then there's a separate set of PowerPoint slides that introduce rate monotonic analysis. And what we're going to look at tonight is this DVD, which essentially assumes that we understand everything that's in these two sets of documents here, and builds on it. You'll have noticed from the discussion that I put in this set of PowerPoint slides on rate monotonic analysis that that there are a whole bunch of crippling assumptions that have to be made, limitations that have to be made about the nature of the real-time tasks before we can apply this particular analysis technique that we're going to be looking at, the so-called Lewin-Leyland's theorem number 1. And that's the one that's got the sum of the ratios of the actual CPU utilizations on the left-hand side of the inequality with the theoretical upper bound on processor utilization on the right-hand side. That's the n outside of 2 to 1 and n minus 1 stuff. That was the result which was produced in the original landmark paper produced by Lewin-Leyland right back in 1973, and it's still only making its way into industrial strength mainstream real-time systems design. As usual, the research in these fields takes quite some time to gather the sort of maturity that's necessary before industrial and commercial contexts will find a place for it. But anyway, that's fine. That'll be your job over the coming years, perhaps. So we find out what a real-time system is in chapter 19. And as I mentioned before, they confuse it a little bit. It's really nothing other than a computer system that's got input and output and processing constraints applied to it by the external environment. That's the important thing. So some other external specification will come along and say that certain operations, input, processing and output operations, need to be done by fixed points in time. And if that system can tolerate the occasional missed deadline, then we classify that system as a soft real-time system. We're not interested in those. If the system can't tolerate any missed deadlines at all, then it's a hard real-time system, and that's the type that we'll be looking at. The video that we're going to be watching now, as I mentioned, assumes that we understand all of this stuff, the stuff that's in both of these sets of documents, and even after it recaps it, it moves on pretty rapidly. What it does do is it relaxes the limitations and constraints that are mentioned in this document that need to be applied to the processes before this rate monotonic analysis stuff can be useful to us. And I mentioned in the lecture that these constraints can be relaxed, but we start with the trivial case of a fixed number, n processes. They're all going to have different priorities. Priorities are assigned rate monotonically. What's the rate monotonic priority assignment algorithm? How does that work? The process with the shortest period has the highest priority. So there's nothing in there for the programmer to do in determining relative importance of the processes. And the programmer doesn't sit back and say, I think this process should be higher priority than that one, for example. The programmer doesn't make any decisions along those lines. They're automatically predetermined by the periods of the processes. And where do the periods of the processes come from? the programmer make them up? Nope. The periods for the processes are enforced on the real-time system designer by the external environment. Whatever it is that we're connecting our real-time computer system up to make it do its real-time stuff, that system is the one that enforces these periodic time constraints. And that brings us to the next problem. This analysis assumes that all tasks are periodic, which is a bit of a limitation, because quite frequently we'll have tasks that actually won't be periodic. But we can deal with that too. We've found a way of incorporating those aperiodic tasks by using a worst case approach. So they can be included in the analysis. The last of the really important limiting assumptions in the basic rate electronic analysis stuff was that the tasks have to be independent of one another. They can't communicate. And we don't like the sound of that at all, because we've just spent several months working out ways in which we can get tasks to communicate. And this analysis is telling us that we've got to have a limited set of tasks that can't communicate. Well, again, those constraints are relaxed in the extended form of the rate monotonic analysis stuff, which is what we'll watch in the video right now. So this video goes for, I think it's 89 minutes, something like that, just under an hour and a half. And the first portion of it covers the rate monotonic analysis in, as I mentioned before, in much the same way as the other two documents do, but then extends the analysis to include the fact that tasks will be dependent upon one another. And they introduce the notion of an entity called a blocking factor. So make a mental note to think carefully about what's being described when these examples get presented in the video, about what this blocking factor stuff is, because that's where we're modelling the fact that real processes will interact with one another. There will be dependencies. There will be times when one process has to wait for another. And we'll be modelling those as blocking factors. Don't be too concerned if after this video finishes that your head hurts and you haven't really got much of the material absorbed, because over the next couple of weeks we'll be looking at in the class session we'll be looking at solving problems using this extended rate monotonic analysis anyway, and I'll be going through the problems. I don't think it's basically a tutorial is what we'll do next week. The whole thing will be a tutorial. And so I won't put any lecture slides and pre-recorded stuff up on UTS Online before next week. What I will do though is I'll remind you to, if you wish to, bring along certain copies of some documents that I'm going to put on UTS Online before next week. You don't really need them, but if you've printed out your own copies, or if you've got your own copies of those electronically, you can make notes and markups on them, which might be useful as I work through the problems and show you how all this stuff actually happens. So, a lot of what we'll see in tonight's video will it'll be like trying to take a sip from a fire hose, the information that's available. But don't panic, because I'll take you through it again much more slowly and methodically in terms of actually applying it to real problems next week. So no big deal. We originally had the Unix and POSIX programming tutorial problems set aside for tonight, but I've only just found those and put them up on UTS Online just before the lecture. So I think it might make sense for you to have a bit of a look at those before next week. They're quite straightforward anyway, and we've got the answers to those. So it might make sense for you to have a look at those between now and next week, and then we'll do those in amongst the problems that we've got set aside here for next week as well. All right, so a real-time system is not a real fast system. It's one that's got input and output and processing constraints applied to it by the external environment. And we've got to build a system that can guarantee and meet those constraints. The good news is we've got reasonably simple mathematical tests that we can apply to tell us beforehand whether or not they'll meet their time domain constraints and requirements, so whether they'll meet all their deadlines. In the bad old days, before this analysis was done, people simply built real-time systems, for control systems, for example, and tested them until they got a certain level of confidence that it would have worked, which of course isn't a scientific way to go about it. The tools weren't available to them until the mid-1980s, around about then. All right, so sit back and we'll watch this video, and Ruth Brown from University of Colorado at Boulder will be our host. This was actually made quite some time ago, but as I mentioned before, it takes a while for these research areas to actually make their way into mainstream use. So even though this material looks pretty dated, it's not. Yeah, that's right. Head hurts already now, doesn't it?
I'm Ruth Ravenel. I'm on the faculty at the University of Colorado at the main campus in Boulder. I'm in the electrical and computer engineering department. My area of expertise is in software engineering within the computer engineering group. I first learned about rate monotonic analysis in the summer of '91 while I was developing a graduate level course for our new Master's in Engineering degree program in software engineering. The text we considered either ignored real-time design or talked about it as more of an art than science or engineering. Much of real-time design does require years of experience, but the material on RMA from the Software Engineering Institute was like a breath of fresh air because it was good mathematics that could actually be taught, and it was practical. I worked my way through the SEI material that was available at the time and developed a few lectures to give an introduction to rate monotonic analysis in the course I was developing. The Software Engineering Institute asked me to work with them to prepare this video with that same introductory material. Much more information is available now in the Rate Monotonic Analysis Handbook from the Software Engineering Institute. For information on how to obtain a copy, write to the address that will be displayed on your screen or call the phone number that's shown there.
Don't bother doing that.
As I work with people who are developing real-time embedded systems, from small products to large, complicated defense systems, I hear of a variety of ad hoc approaches in real-time software system design, and even more ad hoc ways of fixing a system that's already been built but is having timing problems. The primary reason for people resorting to similar experiences, rules of thumb, and other heuristics is that's all that's been available. When you consider the kinds of software systems that have been built with so little science available, it's actually quite impressive. But what we'd really like to do when we design systems is to be able to ensure that the timing behavior is acceptable and predictable. And for existing systems, we'd like to be able to analyze timing problems in a reliable, methodical way to discover what's wrong. With rate monotonic theory, we can do exactly that. Of course, there's a lot more to designing real-time systems than just getting the timing right. But just getting the timing right, reliably, predictably, mathematically right, would be a welcome improvement for many. In this introduction to rate monotonic analysis, I'm going to present the basic theory first. Then we'll look at some examples to see how to apply it. But the basic theory is limiting in its constraints. So we'll then look at some of the ways we can relax those constraints and widen the applicability and practicality of the method. Finally, we'll look at a case study of a real product that was missing deadlines in early prototyping. We'll see how the theory was applied to analyze the timing problems and point the developers to the routines that were causing the problems. Before we begin looking at the rate monotonic algorithm, let's consider what the reasons are for a particular task missing its deadline. First, in a quite reasonable situation, is that a higher priority task needs to run, but it doesn't finish in time for the task we're concerned about to also run and meet its deadline. Second, the given task simply takes too long, from the time it was able to begin until the time the deadline occurred. Third, a lower priority task has somehow been able to block the task in question from running. We call this priority inversion. Now then, what we have may be a simply impossible situation where no one under any circumstances using any algorithm could schedule the tasks to always meet their deadlines. On the other hand, if we can identify and limit the sources of priority inversion, we have at least a fighting chance of discovering whether these tasks can meet their deadlines. Let's look at an example of priority inversion. Suppose you have 3 tasks in an air traffic control center. One checks airplane paths and predicts collisions, very high priority. Another refreshes the controller's screen periodically. A third task updates the data on each airplane's location. Clearly, the collision checker cannot be accessing location information while the location updater is changing the information. To prevent this, the collision checker and the location updater share the data resource via a flag or semaphore to lock out the other task when the data is being accessed or changed. And suppose there comes a moment when none of the tasks are running, but the location updater wants to. Since the higher priority tasks are not running, the low priority task begins, and eventually gets to the point where it sets the semaphore and locks out any other task from using the shared resource. The routine that sets a semaphore is traditionally called P for prohibit, and the one that frees it up again is called V for allow. Well, if that makes no sense to you, you're in good company. But they were named by Esther Dijkstra, who speaks Dutch, and it makes perfectly good sense in Dutch. Now, as we all know, Murphy reigns in real-time systems. So, while the low priority task is using the resource, the collision checker task needs to run. It takes priority, of course, and runs, right up until it needs to use the resource that's been locked out by the low priority task, called update location. Well, all right, we'll just let the low priority task finish using the resource, right? Wrong. It starts up again, because higher priority tasks are either suspended or not running. But now, the medium priority task, the screen refresher, wants to run. There could be any number of such tasks. We'll just imagine one. It has no need of that shared resource. The high priority resource is in wait mode, and the screen refresher has higher priority than the low priority task. So it runs carefree to completion. When the low priority task gets the chance, it finally finishes its critical section and frees up the shared resource. And now that both the low priority and medium tasks are finished, the so-called high priority task is going to get a chance to lock the resource and use it uninterrupted from this point on. In other words, the high priority task is finally going to be treated as a high priority task. Before we looked at this example, I said that there were 3 reasons a task misses its deadline. The higher priority tasks take too long, the task doesn't start in time for whatever reason, or a lower priority task is somehow able to prevent it from running. There are many ways to determine the priorities of tasks and many ways to schedule. At the heart of this theory is the concept that the priority of periodic tasks is determined for the most part by the length of their periods. And let me add that this theory has been extended in many directions, including managing interrupts and shared resources, such as we saw in the example. But we're going to look at it in its simplest form first. First principle. A task with a high frequency of occurrence, that is, a high rate, gets a high priority. As a first cut, we'll look at a simple formula where we check the total CPU utilization against a schedulability bound, developed as the first theorem in this body of theory. That is, for, say, 6 tasks, we'll find 6 values, add them together, and compare them to an upper bound for 6 tasks. If the sum is less than or equal to this bound, we'll know that we can guarantee that those 6 tasks can always meet their deadlines. If I were you, I'd be skeptical at this point, but bear with me and I'll get to the good stuff. But as long as I'm making bold claims, let me go on to say that this is also going to lead to a straightforward way to gain useful insight into tweaking existing systems for performance improvement in meeting deadlines. The next slide shows you a list of organizations and applications using rate monotonic analysis. The algorithms and the insight gained from them have been applied in a wide variety of real-world applications. Let's look at a simple problem involving periodic tasks, shared resources, aperiodic tasks, and a task whose deadline occurs before the end of its period. For the rest of the tasks, we'll assume that each task must be completed prior to the next event that triggers that task, that is, prior to the end of its own period. Rate monotonic theory can be applied to all of these situations to determine schedulability, but for now, we're going to limit ourselves to the periodic tasks with shared resources. In this case, a data structure and a comm server. So we have three tasks where the number above a box refers to the length of the period, how frequently the task is required to run. The number inside the box is the amount of time the task would take to run if it were not interrupted. The numbers inside the different shared resources refer to how long the associated tasks spend using that resource. So, task 1 takes 20 milliseconds, but 2 of those milliseconds are spent using a shared resource. And task 2 shares that same resource and requires 20 of its total 40 milliseconds to be spent in that resource. Now, before we get knee-deep in this example, let's get some definitions out of the way. A periodic task is one which is ready to execute at fixed intervals. For now, we're saying that its deadline is the beginning of the next period. And when I talk about a task's CPU utilization, I'm talking about the percentage of time the CPU spends in a single task. That is, if a task has a period of 30 milliseconds and its execution time is 10 milliseconds, then if it's going to meet its deadlines, it will be running 10 out of every 30 milliseconds, or 1/3 of the time available. So we define CPU utilization for task I to be U of I equals C sub I, the execution time, over T sub I, the length of the period. And when we want to talk about the CPU utilization for a set of tasks, we'll just add up the utilizations for each of the individual tasks. One more definition. Priority-based preemptive scheduling refers to a scheduling system whereby you can assign priorities to tasks and the system will preempt, that is, suspend a lower priority task when a higher priority task has requested to run. Let me emphasize that the preemption is based on the priority of the task concerned. This is perhaps different from what you're used to in many interrupt-driven schedulers. In an interrupt-driven system, the interrupting task runs because its interrupt has occurred, regardless of the priority of the task. That's different from this. I realize that many available operating systems don't support priority-based preemptive scheduling, but the method is still useful, as we'll see in a detailed case study, and also, when your group is developing all of the components of a real-time embedded system, you may be rolling your own monitor, and you can make it a priority-based preemptive scheduler. And even if you don't, there are ways to adapt the method to non-preemptive scheduling. Stay tuned. Given priority-based preemptive scheduling, assign priorities to tasks based on the lengths of their periods. That is, a task with a shorter period has a higher priority than a task with a longer period. We're not concerned with how long the task runs within that period. We're only looking at the length of the period itself. Notice also that we're not going to get caught up in arguments about how important some task is. For example, suppose you're designing a system that will be monitoring a surgery patient. Among other things, the system is going to measure blood pressure, say 3 times a minute, as well as heart rate and breathing. You don't have to listen to arguments from the cardiologist and the pulmonary specialist as to which is most important, the heart rate or the breathing rate. I realize in this case I've picked examples of tasks that we would like to be periodic, and if any of them becomes aperiodic, it'll be of critical importance to detect that. But let's use this as a simplistic example for now, and say that the heart rate is going to be in the neighborhood of 60 to 100 times a minute. Respirations or breathing will be, we hope, between 10 and 30 times a minute, and I said the blood pressure would be checked 3 times a minute. Based on the rate monotonic algorithm, how should we assign these priorities? Forget semantic arguments. Look at their periods. Heart rate is approximately once a second. Breathing is about once every 2 to 6 seconds. Blood pressure check is once every 20 seconds. End of discussion. Those are the priorities, period. I'll be giving the reference for the mathematically inclined among us who want to digest the proof, but for now, let me say that the algorithm we're about to look at has been proven to be optimal for static priorities. Now, what does optimal mean? It means that if a task set cannot meet its deadlines with a rate monotonic priority assignment, then the task set won't be able to meet its deadlines with any other fixed priority assignment. And furthermore, if the rate monotonic priority assignment satisfies the CPU utilization bound that we'll be looking at, it's been proven that you can guarantee that the tasks will meet all their deadlines, even in the worst case situation. This priority assignment algorithm is optimal and guarantees schedulability, providing the criteria are met. Now here's the theorem. A set of n independent periodic tasks. I know we're looking at an example with some shared resources, but for now we start simple and look at independent tasks. A set of n independent periodic tasks scheduled by the rate monotonic algorithm will always meet its deadlines for all task phasings, that is, no matter what combination they come due in or when they start relative to each other, if. Now what is this sum? It's the sum of the individual task utilizations, that is, the total utilization. If the total CPU utilization is less than or equal to this expression, n times the quantity, 2 to the 1 over n minus 1. I know you'd be a lot more interested in this if your application happened to involve such a nice, clean world, one with independent periodic tasks. But life's a lot messier than that. Bear with me. We're not going to go into the proof, but you're welcome to pursue it if it interests you. It was published in the Journal of the ACM in January of '73 in an article by Lou and Leyland. By the way, there's also a good overview of RNA in the April '90 issue of IEEE Computer Magazine. Theorem 1 tells us how to compute U of n, the CPU utilization for n tasks. Here's a table of the values for U of 1, U of 2, etc. That is an upper bound on total utilization for a single task, for 2 tasks, etc. Notice that as n approaches infinity, the upper bound is 0.693, or as a percentage, about 69%. Referring to this table then, suppose I have 3 independent periodic tasks whose priorities have been assigned rate monotonically, and I have a priority-based preemptive scheduler, or I can fake it to look like one. I find the execution time of each and divide each by the length of its own period. If the sum of those is less than, well, what is U for n equals 3? 77.9%. Then I know that those tasks will always meet their deadlines, regardless of when they start relative to each other, even if they all request to run at exactly the same time, which is the worst possible case. Let's look at that surgery monitor with some hypothetical values. Task 1 is the heart rate. Suppose it takes 100 milliseconds to measure. If its frequency is 100 times a minute, the period is 600 milliseconds. Task 2 measures breathing and takes 300 milliseconds to execute. Its frequency is 30 times a minute, which is a period of 3 seconds or 3,000 milliseconds. Task 3 checks blood pressure for 3,000 milliseconds every 20,000 milliseconds. Given those numbers, the heart rate utilization is 100 divided by 600, or 0.167. The CPU utilization for breathing is 300 divided by 3,000, which is 0.1. And the blood pressure is 3,000 divided by 20,000, which is 0.15. If these were the only tasks, what would the total utilization be? 0.167 plus 0.1 plus 0.15 is equal to 0.417, which is less than U of 3. Piece of cake, right? After all, the upper bound is 77.9%, and we're only using 41%. But what if priorities were assigned differently? Because the medical advisor believes strongly that it's more important to monitor blood pressure than heart rate. Looking at the resulting timeline, we can see immediately that we'll miss the deadline for recording the heartbeat. In fact, we'll miss 5 of them if the blood pressure has the highest priority, even though our CPU utilization is only 41%. On the other hand, we'd make them all if heart rate had the highest priority. Let's take the 3 periodic tasks from the complicated example that we began with. For now, we're assuming that they are independent even though they're not. The theory has been extended to accommodate tasks that synchronize with each other in some fashion. Let's apply the theorem to this task set. If we find the utilization of each task, we get the numbers in the right-hand column. Adding them, we find the total utilization is 0.753. Is that okay? 0.753 is less than u of 3, which is 0.779. Well, how might it work out? That's easier to see in a timeline format. Let's assume the worst possible situation occurs, that all 3 requests to run at exactly the same time. Here we see task 1 with its period of 100 units and an execution time of 20 units. It has the shortest period and therefore the highest priority. You can see that whenever it requests to run, it takes priority and runs until it's done. Task 2 has an execution time that's twice as long and only comes due every 150 units. There's time for it to run unbothered after task 1 has run. Task 3 starts to run at time equals 60, but can only get 40 units of its 100 units of execution time out of the way before task 1's next period starts, and task 1 gets priority. Then it can squeeze in another 30 units before task 2's next period begins, and of course, task 2 takes priority. You can see that eventually, task 3 gets all 100 units of its execution time completed before the beginning of its next period. So even task 3 has met its deadline. Now some of you are no doubt saying, but wait a minute. If we're switching from task 3 to other tasks and back again, task 3 really takes longer than 100 units. And in fact, how long it takes exactly will depend on how much time it spends in context switching. Good point. Let me show you how we account for that. Look at the worst case scenario. Add in the time for a context switch to the preempting tasks, that is, the higher priority task, and see if they are still schedulable by this theorem. Why don't we need to add context switching time to each piece of execution that the lowest priority task accomplishes? Because you can account for this time in the preempting task rather than in the preempted task. And it's a worst case approach, since adding context switch time to the higher priority task's execution time assumes that they preempt a lower priority task every time they run. Theorem 1 is exciting when your task's utilization is in fact less than the upper bound for that number of tasks. But what if that's not so? What if the total utilization exceeds the bound provided by the expression in Theorem 1 for that number of tasks? Theorem 1 is what we call a conservative approach, because one can have a set of tasks that are schedulable using the rate monotonic algorithm, and yet they don't satisfy this upper bound. In fact, with the right combination of tasks, it's possible to exceed 90% and even reach 100% CPU utilization. A more precise test would be useful. There's a second theorem whose proof was published in 1987 as a technical report by the Department of Statistics at Carnegie Mellon University. The authors were Lahosky, Shaw, and Ding. I'll give you the reference in a minute. This theorem tells us that, assuming we have independent periodic tasks, we can look at the worst case, which is when all the tasks want to start at exactly the same time, and we can guarantee that all deadlines will always be met if each task is able to meet its first deadline without causing another of the tasks to miss a deadline. So what is the worst case? The worst case for independent periodic tasks has been proven to be the case when all tasks of higher priority request to execute simultaneously with the task in question. And if a task can meet its deadline under the worst case conditions, it will always meet its deadline. Formally stated, the second theorem looks like this. N independent periodic tasks, scheduled rate monotonically, always meet their deadlines for all task phasings, if and only if the following formula holds true. Theorem 2 provides an algorithmic way to check each point where a task has been scheduled, from the initial moment when the task requests to run until the deadline for the task with the longest period. If a point before the deadline can be found, where all the work for a given task can be completed, while accounting for all preemption from other tasks, then the task is schedulable. While Theorem 2 is mathematically correct, it doesn't lend itself to easy use by mere human beings, although it does lend itself nicely to a straightforward computer procedure. Human beings, on the other hand, can look at a timeline for the task set and tell the same information at a glance. Before we look at an example, Here's the reference for the proof of this theorem. And now for the timeline example for theorem 2. First, let's mess up the example we've been working with. I've changed the execution time for task 1 from 20 to 40, which in turn changed the utilization from 0.2 to 0.4. If we only had 2 tasks, we'd be okay, since 0.4 plus 267 is 667, and U of 2, our upper bound for 2 tasks, is 828. But the third task gives us a total utilization of 953. Theorem 1's bound for 3 tasks was 779. Whoops. This is a point where it's appropriate to apply Theorem 2. We'll look at the timeline first, so we can find out if they're schedulable before we die of suspense. And then we'll apply the expression in Theorem 2, which is saying the same thing. Looking at a worst-case timeline, we see that all of the higher priority tasks have been able to meet their multiple deadlines, while the longest period task was meeting its first deadline. This meets the criteria for Theorem 2, and since Lahosky, Shaw, and Ding went to the trouble of proving it for us, we can guarantee the schedulability of this task set for all task phasings, that is, all combinations of start times. That floor operator you saw in Theorem 2 actually triggers each of the scheduling points. Is C1 plus C2 plus C3 less than or equal to T1? Fill in the numbers. 40 plus 40 plus 100 is greater than 100. Uh-oh. The first scheduling point is the first deadline of the highest priority task, T1. Since this is the worst case, all tasks requested to run at the same time, and obviously can't all run prior to the first deadline. What's the next scheduling point? Well, task 2 has its first deadline before task 1 has a second deadline. But during task 2's first period, task 1 is requested to run twice. So we have 2 C1 plus C2 plus C3. Is that less than or equal to T2? Well, that's 80 plus 40 plus 100, which is greater than 150. Whoops again. Finally, we try the scheduling points at 2 times T1 and at 3 times T1. Visually, you can see that the tasks are schedulable. So for small numbers of tasks, most of us would sketch it rather than working through these sums. But you might be tempted to make a spreadsheet or write a program to do the work for a larger number of tasks. Notice that it's not okay to just look at the expression for the last scheduling point, namely task 3's deadline, because we would have 4 C1 plus 3 C2 plus C3, which adds up to 380, and that's a lot bigger than 350. The theorem was actually satisfied at the scheduling point that was the end of the third deadline for task 1, which is the same as the second deadline for task 2, namely time equals 300. In our first test for schedulability, we added up the utilizations for each task and checked them against an upper bound. Another way of talking about this expression is that this tells us the schedulability of task n itself, where the sum to the left of n's utilization accounts for preemption from all the tasks whose priority is higher than that of n. The nth term is taking care of task n's own execution time, and we've been assuming that the system would execute in a way that's consistent with rate monotonic priorities. We've played around with timelines as if task switches were instantaneous, although we talked briefly about how to allow for the switch time. And the theorems have all assumed task independence. In a moment, we'll look at how to allow for task dependencies, where a lower priority task can block a higher priority one. Anyone with experience designing real-time systems knows that the assumptions at this point are pretty limiting. Only periodic tasks, instantaneous task switches, deadlines are coincident with the start of the next period. Priorities are assigned rate monotonically. Unique periods are assigned unique priorities. That is, if you have n tasks, you can assign and support the scheduling of n priorities. Then priority-based scheduling is preemptive. Tasks are independent. There's only one processor. And it's even possible to obtain task execution times. The good news is that each of these assumptions can be relaxed to make the approach applicable to a wider range of situations. We've talked about some of these, and we'll address a few more. Let's tackle the notion of dependent tasks. That is, somehow a low priority task affects the completion of a higher priority task like the example we saw at the beginning. This is priority inversion, and it's easily possible for systems to have many sources of this. You'll see that it's going to be of critical importance in determining the schedulability of a task set to be able to identify and model those priority inversions. And doing so will direct your attention as to which ones are necessary to reduce in order to make a set of tasks schedulable. Before we look at how to include this concept in our model of schedulability, let's take a minute to think about some of the things that will cause it. Non-rate monotonic priority assignment. Someone simply assigned the priorities differently. Non-preemptibility. Even though the system supports preemptive scheduling, for some reason there's a low priority task that cannot be preempted by a high priority task. Interrupts. In some systems, the operating system may support priority-based preemptive scheduling, and yet the hardware may permit hard interrupts that take precedence despite the length of their periods, and therefore, despite their rate monotonic priorities. Not enough priority levels. If there are not enough priority levels available in the system to let you assign unique priorities to distinct periods, then two tasks with different periods will be assigned to the same priority, and every now and then the system will give priority to the one with the longer period. FIFO queues, first in, first out queues. Suppose a lower priority task makes a request for a device that's managed by a FIFO queue. Maybe it's a message handler or an event log. If the device is busy, the request goes into the queue. Now a higher priority task preempts the lower priority task, but it also makes a request on the same device. Although this task has higher priority, its request lags behind the lower priority task's request in the FIFO queue. Synchronization. Synchronization is a situation we saw at the beginning, where the collision checking task and the airplane location update task shared a resource, and the lower priority task had reserved a resource needed by the higher priority task. Here's a visual representation of how priority inversion affects scheduling. We see 4 tasks that are scheduled rate monotonically, and the scheduling works. What happens to the scheduling when task 3 becomes an interrupt-driven process? Now we have a task with a longer period, by definition a task of therefore lower priority, taking precedence over tasks with shorter periods. In this particular example, the scheduling still works. Each task meets its deadlines. How can we incorporate this notion, the notion of this kind of situation in our model? That is, how do we adjust those inequalities to include the effect of the time required by the task with the inverted priority when we're trying to decide if the higher priority task, rate monotonically speaking, is schedulable? What we've done so far would have compared the utilization of task 1 to the upper bound of task 1, but that's ignoring the fact that this interrupt-driven process exists. What affects the schedulability of a particular task? Call it task J. There are preemption effects. These are the higher priority tasks that can preempt task J. Since their periods are shorter than J's, they have the potential for occurring many times during a single period of task J. The execution effect. This is the impact of task J itself, and when we're looking at task J in particular, that task occurs once during its own period. Blocking effects. These are the lower priority tasks that have the potential of preventing task J from executing. Such tasks can occur at most once each during J's period. How do we know that? Well, by definition, lower priority tasks have longer periods, and obviously a longer period can't occur twice during a shorter period. Notice that I'm not saying that all priority inversion is bad. Interrupt-driven tasks will have a high priority despite their period length, and they will delay tasks with higher rate monotonic priority. Sometimes, however, they're necessary. For example, some external data may only be available for a brief period of time, and it must be read while it's there. We do have to figure out how to incorporate the priority inversion into the model. Let's look at the following example. We have 4 tasks, but the one that is rate monotonically speaking third in priority happens to be an interrupt-driven task. The notion of the interrupts period being 200 units means that the interrupts come no faster than every 200 time units. That is, the worst case is every 200. If we can schedule that situation, less frequent interrupts will be easy. We see that the utilizations add up to 0.824, which is greater than U of 4, or 0.756. How can we evaluate this situation? We must account for the priority inversion that can affect each task's ability to meet its deadlines. First, let's look at a timeline for the example. Remember that when we introduce priority inversion, we must check each task individually for schedulability. Looking at task 1, we see that it can accommodate both the blocking due to the interrupt and its own execution before its first deadline. So we know task 1 is schedulable. Looking at task 2, we see that it accommodates the blocking, all of the preemption from task 1, and its own execution before its first deadline. So task 2 is also schedulable. The interrupt is simple. Because it runs at highest priority despite its period, it doesn't have to accommodate other tasks. We're only concerned about its own execution. Finally, in checking task 4, notice that all the other tasks, including the interrupt, have shorter periods. They can all occur multiple times during task 4's period. To task 4, they're all preempters. Nevertheless, task 4 is able to accommodate all the preemption plus its own execution before its first deadline. We can see that all 4 tasks are schedulable. You may have noticed that this timeline check is similar to Theorem 2. We can also set up a schedulability model for the 4 tasks based on an extension of Theorem 1. We're really just applying that theorem to determine the schedulability of each task, but we're adding a blocking factor to account for priority inversion. In a schedulability model for task 1, we see that C1 over T1 plus the blocking factor of the interrupt. But what is that exactly? It's the time that the interrupt routine takes to execute, divided not by the period of the interrupt, but rather by the period of task 1. Why? Because we want to know what percentage of task 1's period can be eaten up by the interrupt. By the way, often the problem with interrupt-driven processes is not that they exist at all, but that application-level processing is done in the interrupt routine. All that we need to be in the interrupt routine itself is to grab some data at the moment when it's available, and then schedule the processing of that data in a normal rate monotonic fashion. Back to our example. It turns out that task 1 is schedulable since task 1's utilization, plus the blocking factor of the interrupt's time, still satisfies the upper bound for one task. When we look to see if task 2 is schedulable, we must account for the preemption factor of task 1, the execution time of task 2 itself. So far, it's just like the old Theorem 1, plus the blocking factor of the interrupt, this time with respect to the period of task 2. Of course, the right-hand side of the inequality is for n equals 2. We're only trying to schedule 2 tasks, even though a third one opposes a blocking factor. These terms for task 2 add up to 0.867 in our example. But u of 2 equals 0.828, so already this fails Theorem 1. I want to continue with this approach to show how to think about the interrupt task itself, and also the task whose priority is lower than the interrupt. Meanwhile, let me address a common objection that's raised at this point. You might be thinking, we've already seen with the timeline that the criteria for Theorem 2 are satisfied for the task set, even with an interrupt-driven process. So why are we bothering to wade through the application of Theorem 1 to each task in the set? Well, Theorem 2 is good for seeing when the criteria for schedulability are met. But when they fail Theorem 2, it's not as helpful as Theorem 1's model for finding out why, and for directing our attention as to what to try to fix. What's the real problem? This will become much more apparent when we look at the case study about the IBM submarine trainer system, a real product that failed during early prototype executions. Meanwhile, let's go on with this example. The schedulability of the interrupt task looks a little different from what you would expect to see for a third task. It has no preemption terms because it's the interrupt and it's not preemptible. It has no blocking terms for the same reason. So the schedulability of the interrupt task is simply its own CPU utilization, and the upper bound to which it is compared reverts back to n equals 1. Finally, let's look at task 4. What are its preemption factors? Well, all of the higher priority tasks, including the interrupt. But now the interrupt's execution time is divided by its own period, because it's simply a higher priority task from the point of view of task 4. And the n for this upper bound is, of course, 4. By the way, if you plug in the numbers, you'll see that this task also fails Theorem 1. When we get to the case study of the IBM submarine trainer, we'll look at a technique that can often help when an interrupt causes an otherwise schedulable system to fail both the back of the envelope test of Theorem 1 and the exact method of Theorem 2. This technique of evaluating the schedulability of each task based on its preemption factors, itself, and its blocking factors can be used to model interrupts, non-preemptibility for any other reason, and priorities that have been assigned out of sequence from a rate monotonic point of view. For instance, periods based on pre-period deadlines. That is, suppose a task has to finish at least X units before the end of the period. One way of dealing with that is to prioritize the task as if its period were X units shorter than it really is, rather than giving it a priority based on the actual length of the period. We'll look at another way to handle pre-period deadlines later. An example of a pre-period deadline is when you have a system that must respond to an input event before the data disappears. Data doesn't linger until it changes with the next period. There are, of course, other situations when you might assign priorities in a way that's not exactly rate monotonic. For example, jitter requirements. You may not all be familiar with the term, so let me explain by way of a few examples. Digital sampling of analog data. A submarine sonar system that must chirp at fixed intervals. Control loops where you're controlling the movement in an analog system, and it must be smooth, such as servo motors in an airplane's wing flaps, an automobile's braking system, or cruise control. What do these have in common? Digital sampling has to do with input. Servo control has to do with output, but both are occurring at fixed intervals. That's not quite the same as saying that they're periodic tasks. They are, but they're more restricted than that. It's not okay for the cruise control acceleration increment to occur anywhere within the interval. If you're resuming the cruise control speed after braking to, say, 20 miles per hour slower, you'll find it disconcerting to say the least if the acceleration does not appear to your senses to be smooth. The output must occur at a fixed interval, plus or minus a small permissible amount of variation, and that's known as jitter. Now let's look at the general schedulability model, which incorporates blocking. When we include blocking, we must apply it to each task, considering for that task its preemption factors, if any, its own execution, and its blocking factors, if any. For those of you who may have noticed, let me explain why the blocking factors are a single term. Whatever the execution times are for each of the lower priority tasks that are blocking factors, they each have the same denominator, namely the period of the task in question. So the execution times have all been added together and represented as one term over the period length. For example, in the first line, the blocking factors are grouped as B1 over T1. But remember, an inequality is set up to test the schedulability of each task from task 1 to task n. Once you understand the principles, there are often many different ways to address the same problem. A few minutes ago, I talked about handling a task with a deadline before the end of its period, a pre-period deadline, as something that you might think of as having a shorter period than it really does. Another way of thinking about it is to assign its priority based on its actual period, but treating the amount of time prior to the end of its period by which the task must be done as being a kind of blocking factor. In this treatment, our expanded model applies. That is, in analyzing the schedulability of the task, we have whatever preemption factors there may be, the execution of the task itself, and this chunk of time that's part of every interval for this task, and represents a piece of the interval in which the task is blocked out. It may not use that piece. If that doesn't click for you, think of it this way. For the purpose of analyzing this one task, pretend the task actually takes longer than it does. That is, add to the execution time the amount of time prior to the end of the period by which it must be completed, or the point by which the task must be dormant. If a task with this much so-called execution time is schedulable, then even if it runs at the last permissible moment, it will execute and still have this chunk of time remaining, thus meeting its pre-period deadline. Notice that if you add the dormant time, the length of the pre-period deadline, to the execution time of the task, you only do that when computing the schedulability of the task itself. If you then move on to a lower priority task, the one with the pre-period deadline is a preemption factor, but it is only the normal actual execution time of that task divided by its true period length. So much for examples of extensions of a model. When people are introduced to rate monotonic analysis, a common response is, well, that's all well and good, But I can't do any of these computations without knowing the execution times. And we won't know those till long after we've already designed and implemented the system. In response to that concern, let's pay attention to a few things. First of all, bear in mind that the unavailability of accurate execution times early in the design is not an issue that's specific to a rate monotonic approach. That's a problem that's inherent in real-time systems. And you often create timing budgets in the early design of a system. It's very likely that your timing budget for high-frequency tasks will be pretty accurate. Those are the ones you necessarily will be paying more careful attention to. And even if your budgets are off, you can use the method to decide if the budgeted times are schedulable. Then as better information becomes available, you can plug in the new numbers and find out if your system is still schedulable, or direct your attention to an area to tune. The algorithm is robust to change, which means you don't have to change the scheduling algorithm just because you have different numbers. And if the priorities of tasks change, this method does not require you to invent a new ad hoc algorithm for scheduling, or for analyzing the schedulability of the changed system. If you're using the approach for design, it will focus your attention on the parameters that are most important. And if you're using the approach as a method for analyzing an existing system, the numbers can be obtained, and it will direct your attention regarding where to look to improve the system. And as you'll see in the upcoming case study, it will also tell you when you can stop improving the performance, because you can now guarantee schedulability. There are other valid issues raised by those involved with real-time systems. Many of these have already been addressed at the SEI, and materials are available in the handbook. For some others, work is in progress. For instance, multiprocessor systems, both parallel and distributed. Priority granularity. This has to do with what to do when the operating system you're using in your design doesn't support enough levels of priority. Remember, unique period lengths get unique priorities. Spare capacity assessment. This has to do with figuring out how much of the CPU is realistically still available after scheduling the tasks that had deadlines. Aperiodic tasks. An event may occur somewhere between every x to y milliseconds. If we assume the worst case and call the period x, we know how to incorporate it in our model. Of course, there are other kinds of aperiodic tasks that you can learn about from the handbook and other sources. Overload involves managing the situation where there are too many tasks. They are not all schedulable, but you need to ensure that certain tasks run. Mode change has to do with changes in priority that are tied to changes in mode, such as initialization mode versus execution, or normal versus combat mode. I've already mentioned the RMA handbook. Now here's an idea of what it is. I noted earlier that work on rate monotonic analysis has continued at the Software Engineering Institute. Sometime in '93, the SEI is publishing a handbook that walks through an overview of rate monotonic analysis and has a bibliography for much more detail about the theory. More importantly than the overview, it provides a framework for thinking about timing and concurrency aspects of real-time systems, and hundreds of pages of carefully worked out examples that show how to use the framework and apply it to do the analysis for each situation. At the beginning of this presentation, I gave you the address and phone number that you need to get more information about the handbook. You can also call that number to find out who is currently offering RMA courses that can be delivered at your company site. The IBM DC-1 submarine trainer was an actual project that was not implemented using rate monotonic theory. In its early testing, the implementers discovered that it was missing deadlines wildly. It happened to be the case that one of their employees had been at the Software Engineering Institute working with rate monotonic analysis while these problems were surfacing. Upon his return to IBM, he learned about the problems and the proposed solutions. And as an alternative, he spent 3 weeks applying this methodology as an analysis tool. It turned out to be extremely useful because it helped him discover sources of priority inversion, focused his attention on where the real problems were, and made it clear when to stop. That is, he was able to say when there had been enough performance improvement. One of the most important reasons for examining this case study in detail is that the theory was applied to an existing system that was not a priority-based preemptive system, and it is still useful. Let's start by looking at the overall system. If there had been a submarine in the water, it would have been collecting information about its environment via sonar and other means, and providing this information to the Busy One computers. The IBM mainframe simulated the environment for the training scenarios. It also formatted the data for the submarine software, as if the sensor hardware had been there. Because the Busy One computers used Navy standard communication channels, the IBM mainframe could not communicate directly with the Busy One mockup. However, PCRTs came equipped with IBM-compatible communication channels and also Navy standard channels. The PCRTs buffered the data, processed it, and delivered it to the Busy One computers at the proper time. The PCRTs were servicing requests from both sides. That is, they serviced interrupts from the mainframe, simulating the environment, and they serviced interrupts from the Busy One trader system that was being stimulated by this data. The PCRTs were programmed in Ada running on top of AIX, and this is the software that we're going to look at. VRM is a virtual machine interface to AIX. AIX is the primary Unix-like interface running on top of VRM. Ada RTOS is a runtime system built on top of AIX and designed to support real-time programming in Ada. The application software was written as a single Ada task, driven by signals from the I/O drivers and an interval timer. There were 6 tasks related to 6 periodic events. For each of these tasks, there was a corresponding interrupt process to trigger it. Now we're going to look in more detail at how the application tasks and the interrupt processes interacted. The application was quiescent or inactive until an event signal came from the mainframe I/O, the Busy One I/O, or the timer. When an event signal occurred, an interrupt-driven process set a flag for that event, and if the application was quiescent, woke up the event. The application code would check event flags to see whether an event needed processing. It checked these flags in a fixed sequence using a loop, and therefore serviced them in a fixed sequence. Since the interrupt processing happened independently of this loop, let's look at the following example to get a better feel for the interaction. Let's suppose that event 3 set flag 3. The application software checks to see if flag 1, then 2, then 3 are set. It finds that flag 3 is set and processes that event. While this event's being processed, it may be the case that events 1 and 5 occur. Event 3's application processing is interrupted long enough to set the flags for 1 and 5. When event 3's processing is complete, the program does not go back to event 1, but rather continues on in the sequence, checking flag 4, and then finds that flag 5 has been set. It processes event 5 by running the application software associated with event 5. After checking flag 6, the application software would go quiescent again, unless there was a new signal waiting, in which case it would go back to flag 1 and begin the fixed sequence again. Early prototypes of this system showed that data overruns were occurring. That is, it couldn't handle the flow. Before one interrupt was processed for one particular event, another signal would arrive for the same event. Their initial thinking was that the problem was the CPU utilization. So they developed a 3-step plan to speed up throughput in hopes of avoiding the data overruns. First step, signals were used to pass control from an interrupt to the Ada application software. They identified a technique whereby the interrupt would only signal the application if the application was waiting for one. That way they wouldn't be interrupting this fixed sequence application software when it wasn't going to do anything about the new event just then anyway. 2, they decided to move more processing down to the VRM device drivers, because these drivers were closer to hardware and were written in C. The hope was that this would increase the responsiveness and the efficiency of the channel activities. And finally, they would eliminate Ada and thus remove the need for Ada RTOS as well as AIX. This would require rewriting 17,000 lines of Ada into what was hoped to be more efficient C or assembler. These are standard sorts of things to do when the CPU is being beaten to death and there just isn't enough compute power available. By coincidence, one of the employees returned at this juncture from a year at the Software Engineering Institute, where he'd been working with rate monotonic theory, and he was directed to apply it on this problem before they proceeded with the 3-step plan. Looking at the world through rate monotonic colored glasses, what can we say about the software in question? There are 6 periodic events, even though it's written as a single task. And in this application, each event's deadline is simply the next arrival of the same event. We're not dealing with pre-period deadlines or any of those other variations on a theme that might change our analysis. For every event, there are 2 types of processing: the interrupt level to acknowledge the event, and also the application level to process the event. Notice that though the interrupt level is, by definition, preemptive, the application processing is non-preemptive. And what do we know about our scheduling discipline? Well, it's not priority-based preemptive scheduling. It's a straightforward round-robin algorithm. Now, just for curiosity's sake, let's find out what the total CPU utilization is for these 6 tasks. We can see that the sum of the task utilizations was 54%. Whether you can remember what U of 6 would be, you know that 54% is less than 69%. And 69% was the limit of the upper bound as the number of tasks went to infinity. Clearly by Theorem 1, the back-of-the-envelope conservative method, we should be able to meet deadlines. Of course, that's only true if the conditions of the theorem are being satisfied. What's the first thing you notice about these events? They're obviously not in rate monotonic order. Before we rush off to look at what changes were done as driven by the analysis, let's take a second to see the kind of thing that was causing the data overruns. We know it wasn't the CPU utilization, but what was it? Here's a hypothetical execution sequence of just 3 of the tasks in the original design. We'll creatively call them A, B, and C. The tasks are periodic with different length periods. Notice the key showing interrupt level processing for a given task as being represented differently from application processing for the same task. Suppose event interrupts occurred for B, then A, then C. As each event occurs, its interrupt processing is handled as soon as possible. The application task then proceeds to do task A if it is next in a round-robin loop. Task B's next interrupt occurs, and it's processed. But the system never had a chance to do B's application processing from the first interrupt. It finishes A's application processing, then performs B's and C's, etc. Remember, our initial focus will be to find the effects of preemption, execution, and blocking for each task. What would you do first? Well, of course, if this is to be a rate monotonic analysis, we need to put the tasks in rate monotonic order. So the very first step was to discover the lengths of the periods and the execution times for the interrupt and application processing associated with each event. Since the code was already written, it was not too difficult to get numbers for these processes. Let me explain some notation, and then we'll look at what Theorem 1 has to tell us about the schedulability of the system. Look at the column headers on this slide. C will refer to the sum of the interrupt processing time and the application processing time for a task. CI refers to the interrupt processing time only, and CA refers to only the application processing for a task. Now that the tasks are ordered rate monotonically, what we are calling task 1 has the shortest period at 43 milliseconds and the highest rate monotonic priority. No task is preempted in the sense of having higher priority, but let's look at the blocking factors. For task 1, we have the schedulability test as just an algebraic expression. We'll plug in the numbers in a bit. C1 over T1 is the utilization of the task itself. What's this other term? The blocking factor worst case may be worse than you thought at first. With exactly the wrong combination of timings, the interrupt for event 2 could be processed, and the round-robin scheduler could have just started the application part of task 2 when task 1's event occurs, and also all the others. So the interrupt processing time for each of the events has occurred after task 1's interrupt processing, but all of their application processing will occur in round-robin fashion, beginning with task 3 and continuing through task 6. Finally, task 1's application processing will get a chance. And all of these execution times in the blocking term of the sum are divided by T1 because these are blocking factors affecting the schedulability of task 1's period. Plugging in the numbers, we get 2.47, which isn't even close to U of 1, namely 1. Obviously, the blocking factors are blowing us out of the water. We'll look at one more and then see how various changes began to affect these numbers. In task 2, you'll find there's a preemption factor, but be careful, it's not all of task 1's interrupt and application processing times. Remember, it's a round-robin scheduler for the application processing. The preemptive scheduling only applies to the interrupt processing part of each task. So as a preemption factor, we have C1I over T1. Then there's the execution factor of task 2 itself. And finally, we have the enormous blocking factor, although it looks a little different this time. The denominator is task 2's period, since that's the task whose schedulability we're looking at. The numerator is the sum of all the execution times for tasks 3 through 6, and the application part of the processing for task 1. Suppose task 3 had just started its application processing when all of the other tasks' events occurred, with task 2's event occurring first in that list. Then all of the interrupt processing for tasks 4 through 6 will occur long before task 2 gets to do its application processing. And in fact, since we're in a round robin, after task 3 finishes its application processing, tasks 4, 5, and 6 will also do their application processing. Then the application will check if any more flags remain unclear. Yes, tasks 1 and 2. And because of the round robin design, task 1's application processing happens before we finally get to task 2's application processing and finish the job. You might be thinking, now wait a minute, if task 1's event occurs just after task 2's, and then all of that other processing takes place, isn't it possible that another interrupt for task 1 can occur since it has such a short period? Well, yes, it is possible. And that's why C1I is divided by T1, its own short period. So we learn what percentage of its own period this process is occupying. That will account for possibly multiple occurrences of task 1's interrupt during this time. So, plugging in the numbers, again, it's bigger than 1, so it's certainly bigger than whatever U of 2 is. In short, in worst-case situations, the blocking factor is tremendous. Without making major changes to the product, was there a fairly inexpensive way to get away from that round-robin scheduling? Remember that the application portion of these tasks were all embodied in a single ADA task. What made it round-robin scheduling was that the code for each application followed sequentially. They modified this slightly so that when an event's application code was complete, the product would not go on to the next in line to see if its flag had been set. Rather, it went back to a central point to see if any task's flag had been set. If so, and if the task were higher priority, that task's application code was executed next. What they had in effect was a rough method of preemption. It's not true preemption, but it's a lot closer. For example, if task 3's application were running and the events for tasks 1 and 5 occurred, the interrupts would preempt task 3, same as always, to set its flag. But then task 3's application would run to completion. Then, rather than continue sequentially, the system would go back to check if a higher priority task flag had been set and discover task 1's flag. Then it would run the application part of the task. Now that we've changed the scheduling algorithm, events will be processed rate monotonically. Let's look at the effect that this had on the schedulability of task 1. We have C1 over T1 for starters. That's no surprise. But the numerator of the blocking factor has changed. In what way? What's the worst case situation now? Well, the interrupt portion of any of the other tasks may occur while task 1 is attempting to execute. That hasn't changed. But between the time task 1's interrupt has occurred and the completion of task 1's application software, the worst that can happen with respect to the application tasks is that one of them has to finish, the one that was running when task 1's interrupt occurred. That's why the numerator shows the worst case blocking factor to be all of the other interrupt execution times and the execution time for the longest or max task application code. What happens now when we plug in the numbers? 26.7 is the longest of all the application processing times. Now task 1's inequality goes from 106.1 over 43 to 72.6 over 43, a dramatic improvement. However, since 72.6 over 43 is greater than 1, it's still not schedulable. Similarly, for task 2, we have the inequality that you can see. But now, the blocking factor numerator involves tasks 3 through 6. Task 1 is handled as a preemption factor, divided by its own period length, to get the percentage of time that it takes up, since it can happen more than once during task 2's attempt to execute. Plugging in the numbers on task 2, we go from 1.454 to 1.122, closer. Of course, for task 2 to be schedulable, we have to do better than that. You might be asking something along these lines. I thought you said that Theorem 2 is more precise than Theorem 1. And here we are checking to see if we could satisfy the Theorem 1 bound. Why? Well, I'll grant you that you can write a little program to compute the values for Theorem 2. Suppose you've done that. What do you get with Theorem 2? Well, essentially, it's like the magic 8-ball. You plug in the numbers, then turn the ball upside down and wait for the answer. Yes, or no. But now that you have the answer using Theorem 2, what are you going to do next? Theorem 2 gives very little advice during the analysis process. Theorem 1 gives a much clearer picture of the impact of preemption and blocking factors, and it's much more helpful in directing your attention as to what to do next. Back to our case study. What are we going to do next? We saw in the model that the problem was still the blocking factor. Here's a summary of the tasks in rate monotonic order showing each period length, time and interrupt processing, time and application processing, and the total execution time. Looking at the schedulability model for task 1, what would you investigate? What's a likely candidate? Given that the application execution times figure prominently in the blocking factor, reducing the maximum one should help. When the folks at IBM looked at this, they noticed that tasks 4 and 5 had a lot of application processing time, and the interrupt processing for task 4 was also noticeably large. When the analyst investigated, he discovered that both 4 and 5 were moving several K blocks of data at a time. He decided to change it this way. Instead of moving however many thousands of bytes of data there were to be moved all at once, the task would move 1 K of data and then set a flag if it had not moved all of the data. Then it would check to see if there was other work to be done. When the task had another opportunity to run, it would check to see if there was more to move, and it would then move another K. This made a dramatic reduction in the blocking factor, which we can see when we look at the table again. It dropped the application blocking factors for task 4 from 26.7 down to 4.5, and for task 5 from 23.4 down to 3.9. The 26.7 used to be the max application blocking factor. Removing it would have transferred the honors to task 5 with 23.4. It's been reduced also, so the new winning blocking factor is task 2 with 8.5. Putting the 8.5 in place of the old number, the schedulability reduces to 1.26, which is still greater than 1. You might want to go after that interrupt factor that was so high, but while we're looking at application factors, we'll persist here for a while. The goal is to reduce the max length application time and get it down to a number better than 8.5. The application part of task 2 is involved in I/O. It started several I/O operations simultaneously, so it could do asynchronous I/O and keep those NTDS communication channels working and busy. The task would then wait for all the completions to come back before doing the next step. Obviously, that's a good, efficient use of NTDS channels. However, in a real-time system, when you have a task that waits, there's probably a priority inversion going on, because some task is locking up the system while not getting anything accomplished, and other higher priority tasks are unable to run. The fix was not a difficult one. They switched the algorithm in task 2 from asynchronous I/O to synchronous I/O. That is, it would start one NTDS channel and wait until it was finished. Do you remember that the NTDS communication channels were the ones between busy one lockup and the PCRTs? The task would start the next channel when it got another chance at its priority level. This reduced task 2's application blocking factor from 8.5 milliseconds down to 1.7. It didn't change the total 8.5 milliseconds of execution, since there were still 5 channels to manage. But the amount of time that blocked other priorities was reduced to 1.7. The interrupt processing time was also reduced, because the task now was waiting for, and thus being blocked by, only one interrupt process instead of 5. Now the max part in the application blocking factor is task 4's figure of 4.5. By the way, in case you're wondering, let me point out that when you do the schedulability test for task 4 itself, you still use the 26.7 as the execution time, because that's what it took to move the total amount of the data. But you don't have to use it as a blocking factor. As a blocking factor, it doesn't interfere for more than 4.5 milliseconds of that time. However, how are we doing on schedulability? For task 1, we're now down to 44.5 divided by 43, which equals 1.035. Still greater than 1, but so much better than when we started. For task 2, we get 0.822. U of 2 is 0.828. So task 2 is actually schedulable at this point. Task 3 is 0.594, which is also schedulable, and so are the others. The only real problem left is task 1. Time to investigate that significantly longer interrupt processing task. You can see in the interrupt processing column that 21.5 is much larger than the other numbers in that column. When they looked at their interrupt handler for task 4, they were somewhat embarrassed to discover that it was moving big blocks of data to some region so that the application part could move it somewhere else before operating on it. They were able to take 15 milliseconds worth of processing out of the interrupt handler and move it to the application part. That made task 4's application time increase to 41.7, but the application moved this additional data using the new technique of only 1K at a time. So although the application process increased by 15 milliseconds, the task as a blocking factor stayed at 4.5, and the interrupt processing was reduced to 6.5. What does this do to the schedulability of task 1 now? We had 44.5 over 43. It's now 29.5 over 43, which equals 0.687. And that is clearly well under the upper bound of 1. Success! They actually fixed the algorithm, so it only moved data once instead of twice. But just moving the processing from the interrupt handler into the application process was enough to conquer that last holdout on the schedulability. You might think that since task 4's application execution time went from 26.7 to 41.7, we should also look at the schedulability of task 4 to see if it changed. However, remember that task 4's schedulability will be based on its total execution time. Since 15 milliseconds moved out of interrupt processing into application processing, the total didn't change at all, and it had no effect on task 4's schedulability. We have a table showing each task's preemption, execution, and blocking factors, and also the schedulability totals for each task. Looking at the numbers in the right-hand column, you can see that all the tasks were schedulable. You may not remember the numbers for U of 2, U of 3, etc. Just remember that as n approaches infinity, U of n approaches 69%, and all of the schedulability totals are less than 69%. Notice that the execution utilization total is still only 54%. With the changes we looked at, the amount of work to be done didn't change. Sources of priority inversion were uncovered, algorithms were changed to reduce how much time was spent in one task at a time. And now, all the tasks are schedulable. We not only know that, we also know we can start. In the actual case study, it took approximately 3 weeks to collect the timing numbers and do the analysis. Do you remember the original plan? It would have involved rewriting 17,000 lines of Ada into another language. Instead, a few hundred lines of Ada were modified. With your new level of understanding about sources of priority inversion, I'm sure you also can see that besides the time spent in rewriting, testing, and debugging 17,000 lines of Ada, the original plan simply would not have solved the problem. Moving the application processing down into the interrupt-driven routines would have made the schedulability even worse than it was. Yet, what they were proposing were common, traditional ways of solving similar deadline problems. In this presentation, we've looked at the basic theory and some expansion of it, and we've looked at this extended example. I hope by now you'd be inclined to agree with me that in the design of real-time systems, guaranteeing schedulability is possible. It's mathematically simple, and it's realistically practical.
All right, thanks, Ruth. Okay, so what we've just done is we've watched that. And as I mentioned, there's a fair bit of information in there, and I'm not anticipating that you'll absorb all of it, that's for sure. But that's okay, that's not a problem. Because what we'll do next week is we'll have one big tutorial session, essentially, where I'll be working through the problems that accompany the video that we've just watched in a set of teaching tools that we've had around here for a while. So there'll be some problems that I'll work through nice and slowly that allow us to practice the stuff that was in that presentation. And we'll do some questions from chapter 19. There's only 2 or 3 that are relevant. And some introductory rate monotonic analysis problems, very simple ones. And we'll have a look at any of these too that we think might be useful. The Unix and POSIX questions are quite straightforward. You can answer those just off the PowerPoint slides. Nothing untoward there. So over here in our course documents folder, this is what we've just covered today. And I recommend having a look over the, at least this one, at least the introduction to rate monotonic analysis before next week, if you haven't already. Don't think many of you have. That's all right. Look over that one before next week. It's important to do that. And bring along copies, either hard copies or electronic copies of these 2 documents. Because even though they say rate monotonic analysis homework documents 1 and 2, they're not homework. They're the ones that I'll be working through in our big tutorial session. So those are the problems those are the documents that contain the problems. That is the focus of that particular activity, problem solving using extended RMA. Those are the POSIX and hard real-time systems tutorial problems there, and the answers to them there. So 4 extra documents that have popped up just since in the last few hours. Who's got some questions? No. All right. Yes. No, it's relevant, all right. If you're building real-time systems, absolutely. In fact, it's only the introductory approach. It's only the first step in modern real-time systems analysis and design. And when we get down to here, when we do this topic, dynamic scheduling techniques, we'll see that rate monotonic analysis and the slightly more general deadline monotonic analysis actually aren't quite as powerful in practice as the dynamic scheduling techniques that we'll look at. And proper real-time operating systems like QNX, for example, has system calls in it that allow us to do that sort of stuff, dynamic scheduling system calls. So yes, it's real stuff, it's not just hand-waving. Yeah. In fact, the QNX operating system that I talked about in that lecture there is actually available as a free download for evaluation and academic use, and it's well worth experimenting with. The GNU toolchain's been ported to it. It's got its own little graphical user interface called Photon, which looks quite slick, and underneath, well, from the user perspective, it looks like any other operating system, but underneath, it comes with all these extra system calls that allow us to do the sorts of scheduling on the processes that we need to with the real-time guarantees built in. So, yeah, it's proper. Or at least, having said that it's available as a free download, I better just check if that's the case. It certainly used to be. used to be completely free for student or academic use. I don't know whether it still is. But yeah, as an example of a real-time operating system, that is one. Not the only one, but probably the best known one. All right. Anyone else got any questions? Yeah, like I say, that's a fair bit of information for your first real taste test of this stuff. Again, I recommend looking at that lecture before next week, just the introduction to rate monotonic analysis, and either bringing hard copies or electronic copies of these two documents along. If you do that, then we'll be up to speed. All right. Well, that might do us then. You don't have to rewrite 7,000